Hello everyone and welcome to this presentation on deep dive into deep learning for multi-level classification. My name is Ankit Ojha and today we will explore the transformative role of deep learning in addressing the challenges of multi-level classification, or we can also call it MLC. We will discuss real-world applications, advanced architectures, evaluation metrics, challenges, and future directions. This presentation aims to provide a clear understanding of how deep learning elevates MLC. So let's get it started. So I will just proceed to the slides here. In this we will be talking about introduction to multi-level classification. So basically multi-level classification involves predicting multiple levels for single instance. Unlike single level classification where each instance maps to one level, MLC predicts several relevant levels simultaneously. For example, in healthcare, a patient might be diagnosed with multiple conditions such as diabetes and hypertension. Similarly, a social media image could be tagged as beach sunset and vacation. Challenges arises due to there could be challenges label dependency, like some labels are correlated like dogs and grass, and there is like high dimensionality. So in this, like, tasks often involve a massive number of possible labels. And we can also there is also challenge is like data sparsity. Some labels appear infrequently in the data set. So, traditional methods like binary relevance and classifier chains struggle with these complexities. This is where learning comes in, providing models that can better handle dependencies, sparsity, and scalability. So now, we will proceed to the next slide. Yeah, this is like application of multi-level classification. So basically, in this, we can see that MLC find its way into numerous real-world applications. For example, like healthcare. In this, like predicting co-occurring conditions for patient. And we can see in social media where automatic image and video tagging as seen on platforms like Instagram and YouTube. And we can also for text classification in this categorizing news articles under multiple topics such as politics and economy. And there is also one real world application is like environmental monitoring. In this, annotating satellite images for land use and ecosystem studies. So these applications demonstrates the versatility and necessity of robust MLC techniques across various domains. Now we will proceed to this next slide here. So this is like a deep learning techniques for MLC. So deep learning has revolutionized MLC with its ability to learn complex patterns. So let's look at key architectures. So like first is like we will discuss about neural networks. So early solutions like BPMLL model label dependencies but struggled with scalability. And advances introduce sophisticated loss functions like cross entropy and ranking losses for better dependency modeling. Second is CNN. So this is like a convolutional neural network. So CNN are excellent for image-based tasks. Models like hypothesis, CNN pooling, SCP, and spatial regularization networks capture spatial and semantic relationship between labels. Third is RNN. So in this, designed for is sequential data. So RNN and LSTMs addresses temporal dependencies. Attentive RNN and sequence generation models improve prediction by dynamically modeling label order. And fourth is like transformers. So transformers like query to label leverage attention mechanism to model intricate label dependencies. So like they outperform CNN and RNN, particularly for text and image tasks, but require significant computational resources. And like fifth one is hybrid model. Combined strength of CNN, RNN, and autoencoders. Hybrid architecture optimize feature extraction, label dependencies, and scalability. So basically, these architectures cater to different tasks and modularities, making them adaptable to various MLC problems. So this was all about this slide. We will just proceed to next one. So in this, like, we will be like talking about applications of multi-level classification. So basically, yeah. So sorry, like this we will be like talking about metrics of evaluating MLC model. So in this, like evaluating MLC models requires specialized metrics. Hamming loss. First one is Hamming loss. So measures misclassification for each label independently. And F1 score like is balances precision and recall, crucial for imbalanced data sets. And like mean average is precision is like evaluates ranking performance, particularly in tasks requiring label prioritizations. So ablation studies are also vital. They analyze the impact of individual model components such as attention mechanism or specific loss functions. For example, studies comparing CNN to transformers so that transformers achieve higher accuracy but at a greater computational cost. Yeah. Yeah. So like the here is like challenges and future directions. So this is all. This slide. In this slide, we will be talking about challenges and future directions. So despite progress, challenges persist. So like first is like scalability. So scalability is like extreme MLC tasks with thousands of labels remain computational demanding. So label noise real for like label noise is in for in like label noise real world data sets often have mislabeled data, so impacting model performance. And third is like generalization. Models trained on one domain struggle to adapt to others. So these are the challenges. And like future research should focus on like hybrid models. So combining architecture to leverage their strength, or like few short learning. In the few short learning is like building models with limited label data. And like one could be like explainability. So is it like making prediction interpretable for end users? So these directions offer promising avenues for addressing exciting limitations and unlocking the full potential of MLC. Yeah. So we will now. So like for visualization, actually in this visualization topic, so like visualization play a crucial role in understanding advancements in MLC. Here are some key examples we have listed here. So like first is taxonomy of methods. So this categorizes traditional and deep learning approaches, showcasing their evolution. And is like performance comparison chart. It's like highlighting the trade-off between CNN and transformers on data set like MS Coco, and is like query to label diagram. So explains how transformers decoders dynamically handle label embeddings. And one is like attention map. So this one is like demonstrate how spatial recognition networks capture label dependencies in images. Like challenges versus solution table in this like aligns challenges like scalability with deep learning solutions such as hybrid architectures. So these visuals summarize the field and offer insights into its complexities and innovations. We will so like I just wanted to conclude like this topic. So to conclude, deep learning has propelled multi-level classification to new heights, addressing challenges that traditional methods could not. From healthcare diagnostics to social media tagging, the possibilities are endless. However, the journey is far from over. Future innovations is in hybrid models, few short learning and explainability hold immense potential for advancing the field further. Thank you for watching. this presentation. If you enjoyed this content or have you any questions, feel free to leave a comment below. Don't forget to check out the detailed article and slide deck link in the descriptions. Thank you so much. I just yeah, thank you. My name is Ankit.